welcome everybody after the coffee break for the last session of the first day of this really nice conference. It's a little different from the ones I usually go to. There's people from many different areas. So first of all, that's great, but also let me know if there's something in there that's too jargony, and then I will clarify it in the middle of the talk. But indeed, today I'm going to be talking about super semi-hybrid circuits on a, well, not new, but on a slightly novel implementation, which is on a germanium platform. And indeed, I'm assistant professor at QTech in TU Delft, but I'm also affiliated to University of Copenhagen currently, and so that's why you may see that on my badge. But my background is in the field of spin qubits, and so the quantum technologies kind of comes in there. So what we work on is essentially the spins of individual electrons, which are kind of carved out of a 2-deck that is confined in a heterostructure. Typically, it was gallium arsenide. Now it is silicon germanium heterostructures, which are have either holes in silicon or holes in germanium as the individual units of quantum information. However, the quantum materials comes in the sense that instead of doing this, you can also go and add more maybe physically interesting systems or system with desired properties into the mix. So for instance, you can add different semiconductors. You can add superconductors. I would like the analog pointer if somebody. Yes. 200 euro per day. Yes. First day free.
Okay. Sorry, let me ask you.
That's
okay.
Yes. So yes, so and we've also seen from Alex, for instance, that you can pattern them into grid and have interesting engineered materials as well, and no doubt we'll see more of that later. But in terms of the quantum technologies of quantum dots, spin qubits and quantum dots, this is something I've been working on for a while, and we work on some of the first kind of 2D arrays, so 2x2 arrays in gallium arsenide and silicon. And in some sense, when you're doing these systems, you kind of want them to be as boring as possible. So we typically work with quite a few different materials. So we've worked with gallium arsenide. We've worked with foundry fabricated devices, the idea to scale them more efficiently. But today I'm going to talk to you mostly about germanium, silicon germanium, a germanium quantum well in a silicon germanium heterostructure grown by Giordano Scapucci at Delft. The reason that I want to make superconductor-semiconductor integrated circuits, okay, there's different things that you can do, which I show you in a bit, but one of the things that's quite interesting to me in the realm of quantum technologies is this idea of using these as building blocks for some interesting circuits. So for quantum dots, we always say that they are artificial atoms, and they are in many ways. So you have a 3D confinement that you can engineer. You have a discrete spectrum. You have the level spacings, and you can also make arrays of them. This is a 2-dot array that you can kind of mimic molecules in that sense. And then taking this analogy a bit further, if you could integrate superconducting resonators or other superconducting systems in this kind of hybrid circuit, you could encode a form of light, so for instance a microwave photon, and you could study, for instance, both the bosonic and fermionic degrees of freedom in the system. And so that's one of the goals of this effort. The other goal is that superconducting resonators add quite a bit to our semiconductor platform. So in a very simple way, we use them to do qubit readout. So just by using very basic tank circuits, we can do 3 microsecond single shot readout. We're trying to get this lower. But they also allow fast probing of quantum devices. So here you see kind of a lock-in measurement of a stability diagram, and here you see kind of video mode reflectometry type measurement. And you can improve this by, for instance, going to dispersive readout with a superconducting resonator. But apart from that, and if you have fast readout, just a little digression to say that in our group we also work on using resonators as fast feedback. So if you can do a fast readout, then you can also, for instance, this is a measurement of qubit oscillations, and you can see that the oscillations die down very fast. This is gallium arsenide, so it's because of the Overhauser field, which varies of the order of milliseconds, let's say. And what we did here was, because we can read out very fast in about 3 microseconds, we could do Bayesian estimation of the background Overhauser field from about 10 to 100 measurements. We can get it down as low as 5. And then we can do feedback on that to do a better pulse such that you can enhance your qubit readout. So a resonator adds a lot, even if you just use it as readout. But if you go further, then you can reach other regimes. So we heard earlier today about different maybe polaritonic regimes you can reach. But for instance, you can have strong coupling to charge and spin, and this is one of the ways in which people envisage distant registers of spin qubits to be coupled by coupling it to a superconducting resonator. This is a paper from a group at Princeton, but there's also other groups that work on this. If you turn it around on your head and you think of what can the semiconductor add, you can see that, for instance, if you embed 2 quantum dots in a cavity, and this is an experiment by indeed Jason Pettis' group quite a while back, if you then kind of drive this tunneling in the dot, and indeed you just set the biases such that you're not actually driving it, then you see that there's a form of lasing that takes place. So when you have the dots in this cascade, you see a gain of around 1,000. And so there's also kind of a lot of you can have emission into the cavity, and you can have you can engineer different regimes. And indeed, as I said before in the analogy with light, you can not only add a single resonator to a chain of dots, but you can make an array of resonators. And recent experiments in Maryland and in also in Pasquale Scarlino's group have shown that, and also Christian Anderson's, that you can very nicely engineer, for instance, bots or bands by making the right array of resonators. And so, this is an experiment from the Sholkov group where they engineered a vibronic mode by having 2 resonators and a transmon. So you could really model, for instance, the environment of a molecule and engineer it. And on the dot side, there's been experiments, for instance, in the Velders group at TU Delft, where they have shown that indeed you can kind of model molecular interactions, for instance, by using a 2x2 array of germanium quantum dots. So, and in my group, we're working on doing resonator fabrication. I won't go into that too much in this talk. I focus on the approximatization, but we're working on arrays of superconducting resonators, but also kind of small footprint, high inductance microwave resonators made out of, for instance, niobium tinitride, with the idea being that you can, first, for one, you have a compact element so that you can make a bigger array. And then second, you can also, with the high kinetic inductance material, you can raise your coupling constant, which is proportional to square root of that. And so you have a higher coupling to your quantum dots. On the dot side, for a while, we've been working with the gallium arsenide dot, so I won't go into this at all. But my point in showing this to you is to say that we know very well how to make dot arrays this is one where you try to simulate some kind of triangular lattice. And you can very easily populate, for instance, it may be hard for people to see in the back, but you can populate individual, so you can populate the left two or the bottom two or the right two, and you can very finely control the tunneling and the spin state and other things of these arrays. And then semiconductors and quantum dots can also add parametric interactions to superconducting circuits. So this is some work from the Higginbotham group, and this is some work from UCL group, where they show that you can use this kind of embedded quantum dot or semiconductor junction as a parametric amplifier, for instance. And then I won't go into this, and you will hear a lot of it tomorrow, but you can also, of course, look at Andreev spin qubits and gate mons, Josephson junction arrays, and these are just some of the things you can do with a material that can host both superconductor and semiconductor interactions. And so, to give it away, the platform that I'm working on currently is the germanium platform. And one of the reasons that people give to move to this platform is that in current 3.5 materials, which have been extremely successful, I think you hear about them tomorrow, the idea is that there are nuclear spin limitations to these devices. And this is from Marta, who is here, and this is from the Yale group, where they conjecture that this nuclear environment is not great for the decoherence of a promising platform, for instance, such as Andreev spin qubits. And so one of the reasons you may want to go to germanium is indeed because it is a group 4 material. So you can potentially isotopically purify away the nuclear spin. And here I have a little thing which indeed may not be very easy to see, but there are a few reasons why we like germanium. So one thing is that by working with heterostructures, as Giordano does, you kind of lift away the heavy holes and you have a separation of the light hole heavy hole. Then you have a low effective mass in germanium, which is something that silicon gives us a lot of headache because due to the high effective mass, you have to make very small confinement, and you're at the kind of edge of your lithography, and so you kind of end up with low device yield. You also have this valley degeneracy, which we saw previously that can you can get around that, but we like that germanium doesn't have these valleys to lift your spin blockade, for instance. And then, of course, you can isotopically purify germanium. It is non-piezoelectric, so that is something that can also lead to the loss of resonator circuits. And proximatization works. And this last point is something that I want to convince you of today. You notice that I put this part in black. This is because, depending on the flavor that you're interested in, this can be good or bad. If you're a physics person, then maybe you're excited if you have a gate tunable and direct Rashba interaction. But if you're a person who likes their semiconductor vacuum, then maybe you want silicon. So, it depends. So yeah, just to go a little further, why do we care about isotopic purification? You've probably heard it enough times that it's annoying to hear again for those who haven't heard it. This is a picture of natural silicon qubit oscillations from the Morello group. And you see that it decays in kind of this sliver of time, while if you work on purified 28 silicon, even a little epi layer, your coherence just goes on and on and on. And so, I think it should be stated that germanium is kind of, it's in this nice sweet spot between something that can host superconductivity and also spin zero isotopes. In terms of non-piezoelectricity, we expect that there's lower losses from making resonators on top. There's some hints in the field that this may not be, there may be other things limiting the quality factor of resonators, but we hope we can get over this, but at least it's not piezoelectric. And lastly, the idea is that if you have the Fermi level pinning that you have in these germanium structures, you should expect to have proximatization working. But of course, it's one thing to proximatize a material and another thing to do it in a clean way such that you have this Andreev reflection and a transparent interface. Because that's really what you need for many of these kind of quantum coherent applications. So there's two ways that people are pursuing this, probably other ways, but the two ways that I'm going to talk about. One of them is, I think Georgios Katsaros at IST has tried, which is to etch away up to the quantum well and then add aluminum and niobium, which has a higher critical temperature on top. And then the way that Giordano Scapucci at Delft actually first tried out, and it succeeded really well on the micron scale devices, which is to put platinum on top of the heterostructure and then anneal it such that platino-germanosilicide is formed and goes down and contacts the germanium. So this forms an ohmic contact. And in fact, most superconductors, well, a lot of superconductors and normal metals seem to form this kind of easy contact in germanium. So that's also nice. And so we do the same thing, and this is the process of fabrication and diffusion. So indeed, you put some resist, then you put your platinum on top, and you anneal it down. And here I've done this annoying thing where I've drawn it diffusing outwards, but here is Giordano's paper where by doing a cross-sectional TEM, he's shown that actually it actually pulls inwards, if anything. So this is actually quite good because it means that you're not now restricted by your kind of splaying or your diffusion, but you're just restricted by your E-beam resolution, which is nice. And so this is the device that we're working with, and it's a bit complicated, so I try to walk you through it. So we have two sets of double quantum dots and a charge sensor. The blue areas are superconducting regions, and this part is where we will talk about our proximatized quantum dot. And in the center, we are able to make, for instance, a patch of superconductor, a grounded superconductor, or a gated semiconductor, or other things like that. And the way we do it is by first we anneal in these blue regions, the platinum germanosilicide, and they superconduct. Then we add oxide. We put the first layer of palladium gates, another layer of oxide, and then the barrier gates on top of that. So that seems to work pretty well. And if you ask why are we making this device, then okay, it's a pretty versatile device. You can look at, for instance, Cooper pair splitting. You can look at proximatization. You can look at superconducting behavior. You can look at quantum dots. But the kind of one of the goals that we have is to kind of see if you can couple a spin qubit across kind of this medium range link with a medium range link. And there's some architectures that have been proposed, this one by Quantum Motion, where you can actually tile out on an entire chip what it will look like if you have such a link. So that's the idea is that this will form a coupler between these two qubits. And so just to show you that I didn't make this out of my head, this is indeed something that Leins and Flensburg talked about in 2012. That if you have control of the dot energy levels and tunnel couplings, which we do, you can indeed form a 2-qubit gate, both with a loss de Vincenzo or a singlet triplet implementation of a spin qubit. And recently, actually, Klinova and Loss also worked out in detail the fidelities you can expect from a 2-qubit gate using a superconducting coupler. So what can we show in our device that is cold in the fridge? So if you look at this part where you have two quantum dots and using this guy as a charge sensor with the RF reflectometry circuit connected to it. So the RF charge sensing works out of the box. It seems to be very clean. This we also know from, for instance, germanium spin qubit research from TU Delft. The colors are a bit weird in this monitor, but for instance, you can see that we can deploy the last hole, which is nice. So you can do single particle physics if you so desire. It's really not very visible, but trust me, there are these lines here. But what's also nice is that if you look at the central part of the device, and we have a version with a top gate on top, then you can actually turn on a supercurrent and have kind of these coherence peaks on the edge. And so you can set up superconducting transport through this center patch. You can also set up multiple Andreev reflection, which you can go up to, let's say, 5 peaks. And this kind of gives you assurance that this is a somewhat transparent system. And so, you know, you don't etch at the system, which is good, and you don't create disorder that way, but then by annealing in, you're also not damaging it so much, hopefully. The other encouraging thing is that in the center patch, you see that you have a critical magnetic field of up to a Tesla, and we'll see this is repeated also in the other patch. And then the the in-plane fields are also a bit lower, about 0.5 Tesla. Really sorry about the quality of the colors here, but yeah, we can look at it later if someone wants to. Maybe it's just me from this angle.
No, yeah, it's good actually.
Yeah, okay, great. To me, it looks very strange, but
I think from this angle.
yeah. Great, that's great. So if you now look at the sensor dot here on the sensor in the side with the RF circuit coupled to it, then you can see that the only superconducting region here is these annealed in source drain leads of about 40-ish nanometer wide. And now you see that if you start tuning the magnetic field, then when it's at 0, you indeed still see a supercurrent, but then you slowly can turn it off by going to 700 millitesla, which is, you know, beyond this in-plane field that you see here. And so what is nice about this device is that these 40 nanometer leads induce superconductivity, and so you can in fact dream about having a system where you can bring superconductivity providing leads down very close to parts of your device, and you can maybe make more intricate devices than you can make by etching. So we do have this center dot that we can proximatize, and you can destroy that with magnetic field. But what is also encouraging is that by changing this right barrier, we can also, so we fix the right barrier, left barrier, and we move the right barrier. And you can see that even by moving the barrier and go from a superconducting state to a quantum dot Coulomb blockade state. And this is pretty nice because you want to be able to do this switch with a gate rather than by using a magnetic field, which, for instance, you can't pulse. So that's a nice, nice result, and that seems to work. The next thing that was exciting and that we can see is that you actually can see the signatures when you turn to this intermediate tunable coupling. You can see signatures of singlet and doublet states, and we believe we are in the YSR limit for this, this experiment. And so we try to, we find this in our plunger gate versus barrier gate space. And we try to tune from the doublet to the singlet, and we believe that's what we're doing. We do some modeling as well, but I don't really show that here. And so what's nice is that you can indeed get to the type of states that people use for instance, maybe doing an Andreev spin qubit. You can look at the charging energies versus the gap and things like that, but it's nice that you can have these controllable bound states, for instance. Even in this proximatized system, you still see an out-of-plane critical field of about 900 millitesla, which is pretty good. That's pretty, I would say, encouraging to be able to do some experiments in this kind of intermediate range. And there's some intriguing hints that we see of a subgap spin splitting. It's slightly strange because you not only see a splitting on the dot, but you also see a bit of a splitting on the superconductor side. And that was a little difficult for us to understand. I modeled it using a zero bandwidth model, and we had to add a kind of G factor on the superconductor. So it could be a low-lying subgap state, or it could be the gap itself. The interesting thing is that with these X-germanosilicide superconductors, they're not super well understood. And so I believe this is something that we will slowly start exploring afterwards. We also see an anisotropy in magnetic field, and this is something that's expected in for germanium. It's seen also in germanium quantum dots and for spin qubits, but it's not maybe so expected in these kind of hybrid superconductor where the superconductor has kind of renormalized the G factor. And so this was also a bit surprising to us, but yeah, we have to explore it further. So to conclude, we've been exploring the germanium platform because we want to make these circuits of superconductor and semiconductor systems. We want to get to a coherent, quantum coherent, transparent interface, and we want to be able to make nice dots and nice resonators. And so what we have achieved is that we can see superconductivity. We don't have to do MB growth or epitaxial matching. We have a group 4 material. We can get down to the single hole limit. We can make kind of an SNS junction and a SQDS system. And we are currently fabricating resonators on this system, and the paper is out on the archive. And just I would like to say that these are the students in the lab who've done a lot of these experiments, and they were also done in close collaboration with Ferdinand Kumet's group when I was in Copenhagen, and it continues in my lab now in Delft. So, thank you.